We're going to try to use inviscid flow theory to develop ways to predict pump performance. So we want to be able to predict the head, the net head that the pump can produce, the power delivered to the fluid, the efficiency of the pump, or maybe the volumetric flow rate based on design parameters of the pump. So here's the way you do that. Now there are two ways to approach this kind of analysis. Obviously, the first is not to use inviscid flow theory; it's to use computational fluid mechanics. So go and you break out your computational tools and try to model the actual fluid flow with all its viscosity effects in a real pump design. But perhaps you want to make an initial analysis without doing that kind of detailed computational fluids work. And this type of inviscid flow theory allows you pretty quickly to develop some idea for how your pump's going to perform. And generally, it seems to be accepted that for this type of pump analysis, you might be able to get within 25% of the actual pump performance just using this fairly simplified approach that we're going to outline in the next few lectures. So the critical design parameters, we're going to take a look at a dynamic impeller pump. So this is going to be a pump that uses a rotating set of blades to push fluid around and to drive the fluid. So imagine that there's a rotating axis here, rotating with an angular velocity omega, and there's a blade here. So this piece here is the blade, and it has an inner tip that is at a radius 1 away from the axle, and an outer tip that is a radius r2 away from the axle, and the blade has angles, and that blade angle may change as it goes from 1 to 2, but it starts out at beta 1 relative to the surface of rotation here, or the tangent to the motion of the blade, and then the beta 2 for the outer edge might have a different angle. And so based on those design parameters, we're going to try to predict these values here. So the first thing we can observe is that the motion, the speed of the blade tip, U1. So U1 is the speed of the blade tip. And that's the 1 position, so that's the inner radius position for the blade. And you can see that the speed of that is going to be equal to omega R1. So that's classic, just dynamics. You have the radial velocity times the radius is going to give us a speed of that inner blade tip. So then we're going to lead to an overall velocity of the inlet V1. So if you imagine that the blade is moving with that speed, that's going to drive fluid at this point upward as the blade progresses. So that's going to cause a motion in this direction for the fluid as it drives both up as the blade passes under it, and generally that we're going to label that guy W1, and then we're going to have a velocity V1, which is the sum of those two things, which is the true velocity of the fluid as a result of the blade motion. So the blade motion is going to drive the flow. The blade is going to, imagine a particle of fluid sitting here minding its own business. The blade comes whipping under it with velocity U1. And because the blade is angled, that particle of fluid has to travel up the blade in this direction to move in that way. And that's going to lead to an overall combined velocity of V1. So that's our goal here. Obviously, you have the same idea at the outlet. You have the same kind of thing. The particle of fluid is now, the blade is moving faster at velocity U2. That's going to be quicker because R2 is bigger than R1. So of course U2 is equal to omega times R2. So that's going to be going, and so that's going to be flying along at some U2 velocity, and then the angle of the blade is going to perhaps be slightly different. So we'll draw it here. Maybe this is the angle beta 2, and so that's going to cause the fluid to move both outward and, upward and this way as well as it gets pushed back and up. So that's going to be the same kind of thing. And if you were to draw this as V2, so you'd have some kind of W2 here, and then it would be a combination of that and this would give you this V2. So those are our basic velocities that we're going to worry about. We're going to about velocity going into the domain here. We're going to worry about velocity tangential to the surface, and all those things are going to affect our fluid and lead to us to be able, we hope, to figure out how much fluid's actually going to enter this system in as we rotate the blade faster, as we change the angle of the blade, as we change the radius of the blades. That's our goal.